Buenos dias, children. Welcome to our video.
A1! To identify key areas of morphological change along the length of the beach.
Aim2! To use beach profiles to identify where longshore drift affects the beach.
Aim3.
To identify how the Alcantara River impacts beach morphology. Objective 1.
Okay.
To take multiple transects of the beach profile.
Consistency. Let's go right up here.
Objective 2.
To note any key features in sediments or surroundings.
Objective 3. Visually identify areas of topographical change.
Oh, nice.
Hey, it worked.
Objective 4.
To measure changes in angle along the beach transects. Objective 5! To identify external factors influencing beach morphology.
This diagram is a base map of our study site with Taormina in the north, Gardenia Naxos in the middle, and the beach of the Capo Schiso to the south. The area we studied can be seen in green and covers an area of approximately 1.5 kilometres along the beach. We can also see the main two rivers, the Alcantara in the south and the smaller Fiume de Alcantara in the north. The green arrows show the current process of longshore drift flowing from the north of the Bay of Gardenia Naxos, collecting in the south, and the prominent wind directions can be shown by these orange arrows. Giovanni Randazzo is a main researcher of the Bay of Gardenia Naxos. His work also extends to the Alcantara River. However, there is very little literature on Capo Schiso alone. Randazzo's work mainly covers the effect that longshore drift has on the Bay of Gardenia Naxos. Since prevailing wind direction is directly into Gardenia Naxos, there is high longshore drift from the north to the south, and there's been a number of mitigation attempts made to protect the beach. Randazzo focuses mainly on the management of Gardenia Naxos and the effectiveness of the management solutions. He also covers the Alcantara River and how the river delta would have looked prior to the lava outcrop. So he hypothesises that the river delta would extend out past the lava outcrop, potentially just into the Bay of Gardenia Naxos, and therefore the riverine deposits would build the beach of Gardenia Naxos, creating a much wider beach than what we see. However, it is also argued that longshore drift with this prevailing wind direction would still be great, and so there would be a battle between the power of the Alcantara and its deposition against the erosive power of longshore drift. There is huge scope for our project in the research field at present, as there is no single one paper that defines longshore drift and its factors in relevance to Capo Schiso. There is very little work done on Capo Schiso alone. There are papers that go in detail about the factors that influence longshore drift singly, such as the rivers, the lava flow, the management of Gardenia Naxos, tsunami risk, longshore drift and uplift, although there's no paper that ties them all together as we're trying to do in this project. So river flow patterns before and after the eruptions are covered in detail by Branca and Ferrara, and these can be applied to the Alcantara Gorge and in some part to the Fiume de Alcantara. Gardini Naxos and its management is covered in detail by Randazzo. He also ties together the effects of Alcantara Gorge had the lava flow not happened on Gardini Naxos, and Clayton focuses mainly on the sediment budgets and the science behind the cohesion of particles and how that affects longshore drift. Tsunami risk from the Messina Strait is covered by Papadopoulos. He tries to put together a tsunami risk assessment that is applicable to Catania. We can assume this also applies to Capo Schiso, as it's not that far up the coast and will be affected in the same way as Catania, although we must take into account the beach morphology changes and that will alter the accuracy of his predictions. Longshore drift is covered in detail by Hashimoto. He measures long-term measurements of longshore drift in a different site, although his methods can be applied to Capo Schiso as the methods of longshore drift are similar. It's the influencing factors differ. And then lastly, uplift and coastal emergence are covered by Firth et al. And he points out that uplift is a long-term process, and although we don't see much of its effects on longshore drift at present, there's a huge potential with high uplift rates that longshore drift will be affected.
We started at the Alcantara River runoff because it displayed coastal dominant features. We then moved towards the Alcantara River estuary to understand how longshore drift had affected the Capo Schiso beach in between these 2 points.
We recorded the bearing of each transect and coordinates. This was done to provide empirical results and so that further analysis could be completed later using these coordinates. We also wanted to make sure that our measurements were based on a perpendicular transect to the coast.
We took samples from the top, middle and shoreline of each transect. This was to keep all the results fair and so that changes in sediment could be analysed from 3 points on each transect.
We visually determined breaks in the slopes and measured the length along the transects at which these occur. These were the measuring points used to determine the profile of the transects.
Nice.
Okay.
Using a tape measure and Adam level to measure changes in slope angle from each determined point along the transect. Ideally we would have used ranging poles to avoid errors, but the same two people were used each time to keep it as empirical as possible.
At each transect we took notes on the beach sediment dispersion, beach condition and vegetation and surroundings that may have affected the beach morphology, to understand where the sediment may have come from, how eroded they are, and where they have been deposited. We also took note of the tide as it would affect the length of the transect and any vegetation and rocks as they can influence longshore drift.
We continued this process at points of clearly visible morphology change along the length of the beach. We were using observational sampling, but at the same time we didn't want to skip too much of the beach and risk ignoring changes in morphology.
We later used graph paper to plot beach profiles at each site. Ideally, the x-axis would be consistent amongst the transects. However, the transects varied in length greatly and it was not feasible for the purpose of this video.
The sieving was completed with the same sieve sizes and shaken for a minute in total for each sample. The mass retained at each stage was recorded and the percentage of total mass of the sample calculated. Any observations rocks too large to be sieved were made, but due to the sheer number of them, precise measurements could not be made as it would have been too timely.
In order to determine the different length, slope, angle and visible features at each transect, beach profiles have been constructed for each of our 28 sites between Fiume Alcantara and the Alcantara River mouth. These factors allow a long beach profile to be compiled to investigate how each of the sites between these two spits differ. Our first transect was the area protected by the outcrop of basaltic lava, which seemed to show larger amounts of deposition but lower levels of erosion. The largest levels of erosion were shown in this area here at the shoreline, which is shown by the steep cliff edge here and the the sharp change in slope over a short length, and it's also shown through the gradient of sediment sizes and sediment roundness as you go from the bottom of the transect to the top. By the time we reach transects 3 and 5, the effects of longshore drift are more noticeable, with there being a band of larger deposits in the middle, here in transect 3 and here in transect 5. Transects like 7 and 9 hint at steady, constant erosion and deposition as a result of longshore drift. See from the map here, transect 11 was quite special as it was between two what seemed to be man-made barriers of basaltic rock, so it had protection from both sides against longshore drift. And when looking at the transect for 11, you can see the influence that managed lava or those managed rocks have had on the beach profile. It's very steady, there's no breaks in slope. After this managed part of the beach, at 11 and 12, transects at 11 and 12, the evidence for a very longshore drift dominated sandy beach is observed for the next few transects, like this one, which I believe is 13 and 15. But when you get to 17, something interesting is observed. There's a large spike in angle and drop to create this trough here. As well as this, a large amount of bamboo debris was loose in this area, which could suggest that there's been a recent storm. At transect 20 onwards, the gradient of sediment shifts to show the type of grading we would expect at this sort of beach: larger deposits at the shoreline and finer sediments at the tops of the transects. Also, the deposits are observed to be very well rounded here. Along transect 21, we can see that there's a general sloping up to a plateau, which could suggest that all the erosion is happening here while nothing has reached up here in a while, which is very similar in transect 23 also, in the same ballpark, about the 30 meters, 40 meters. There seems to be a general sloping off into the beach. Moving into the last full transect, sediment starts to get coarser and slope angles start to plateau into a flat plane. This is transect 25. It's plateaued into this plane as we get closer to the Alcantara.
Percent of the material passed through to the number 25 sieve, which has an opening of 0.71 millimeters. 94% of the material stayed in the sieves between number 10 and number 60. %5% of the sediment passed through to the final sieve size here of 250. Strangely, the sieve size before of 120 only had 3% in, whereas the one before that, number 60, had 31%. Then larger sediment found towards the sea, with only 1% being smaller than the number 25 sieve, and the number 25 sieve having only 63% of the sediment inside it. In this sieve again was very large in size, with only about 1.5% being smaller than the 25 sieve going through. The entire transect seemed to have larger sediments here, with again only about 1% of a sediment being smaller than the number 25 sieve going through, even at the top of the transect. Sediment at this part of the beach on Capo Schiso seemed to be a lot smaller, with the sediment being from sieve size 25 down to 250, with about 22% of sediment passing through at each one. Largely medium-sized sediment found in the middle of this transect, with 78% of it falling in the 25 sieve. If we find our way to the top of this transect, we find that the sediments got a lot larger, with 96% falling in the first two sieves. So it was mainly medium-sized sediment found at this site, with 72% falling in the 25 sieve and 18% falling in the 60 sieve. Very similar results moving into the middle of this transect, with 77% and 18% in the 25 sieve and the 60 sieve respectively. Then at the coastline of transect number 20, we found that 95% of the sediment fell into sieve number 25, which is medium-sized sediment. At this next transect by the sea, the sediment was a lot finer, with 66% falling in the first sieve and 30% falling in the second sieve, with only about 4% falling into the other sieve sizes. The sediment got slightly larger moving further up this transect, as the sediments went into the number 10 and the number 25 sieve respectively, with about 75% and 13%, with only 2.1% in the smallest sieve, compared to the 66% earlier. In the number 10 sieve, we found 66% of the sediment. In the number 25 sieve, we found 26%, and 6% in the number 60 sieve. So it was mainly medium-sized sediment found at the top of the transect.
The beach here at Capo Schiso is one of Sicily's main tourist resorts. With rapid urbanisation from the late 70s to the mid-80s occurring, the morphology of the beach has changed drastically over time. This video of the beach taken in July 2018 shows rows of carefully placed beach umbrellas for use during the summer. The constant moving of the sand to make way for tourist activities can and has in the past caused the beach to recede. This video shows the beach in July 2018. It shows numerous hotels built both behind the beach and some on the actual beach itself. This image was taken in May 2013. Here the coast is built up more directly south of the river mouth, indicating more river depositional activity occurring in this scene. The river tapers off in a northeasterly direction, narrowing as it reaches the shoreline and flowing into the Strait of Messina. The beach itself also narrows in a northeasterly direction, indicating that beach recession activity occurs on that side of the river mouth. This image here was taken in May 2015, showing very high discharge rates with a lighter colour and more deposits brought down to the river mouth. This drastic change may be due to cyclonic activity. Cyclone Kendressa occurred between the 7th and the 8th of November 2014, making landfall in Malta and parts of Sicily's eastern coast. The beach at Capo Schiso was therefore in the pathway of the cyclone. Maximum sustained winds were 23.7 meters per second, and the minimum mean sea level pressure recorded was 984 hectopascals. After the hurricane passed Malta, it began to travel in a north-northeasterly direction. It eventually made landfall on Sicily's east coast, with maximum sustained winds of 30 knots. On the 8th of November, over 100 millimeters of rain fell over the eastern part of Sicily. Cyclonic events such as this one lead to excess stormwater, increasing the rate of discharge. As shown in this image, the water is flowing at a much higher rate than in the previous scenes. With the effects of cyclonic events most severe months after the event, this image was taken 6 months after the hurricane, showing the water has a lighter colour, and this suggests that the excess stormwater could have mixed with treated sewage during the hurricane from the sewage plant located on the right-hand side of the river. The third image from July 2018 shows beach recession occurring and less vegetation in the riverbed itself.
Regional setting. The Sicilian Maghrebian Fresh Belt in the early Middle Pleistocene for deep lake succession, deposited on the flexure margin of the Hyblean foreland succession, is currently deformed by detachment faults related to the recent frontal migration of a fresh belt, as response to the approximately north-south compressive regional tectonic regime. Since the Middle Pleistocene, contractional structures have been coupled with oblique extensional faults formed across the western Ionian basin. Figure shows tectonic sketch map of eastern Sicily and Ionian offshore. The Mount Etna volcano, red area, lays mainly at the top of the Sicilian Maghrebian collision zone, a fault and fresh belt sandwiched between the Peloritani block in the north and the Hyblean foreland in the south. The investigated area is on the left side of the top legend, what is in light blue color, meaning there is recent alluvion and slope deposits. The sedimentary substratum of a volcanic edifice outcrops south of Mount Etna and locally along the Ionian shoreline, at the front of the Sicilian Fault and Fresh Belt. It is made up of a lower Middle Pleistocene forty succession of marine, bluish, mostly silty clays with rare intercalation of fine-grained sands and volcanics, up to 600 meters thick, evolving upwards to tens of meters of cross-bedded, yellowish quartzo sands, locally named Terre Forte, of fluvial deltic environment. The volcanism in the Mount Etna region was concentrated along the Ionian coast between 220 and 120,000 years ago, represented by plugs of columnar lavas and proximal pyroclastic deposits. Multiple studies indicate that the eastern flank of Mount Etna volcano has been sliding seaward. The sliding area is confined to the west by the northeast and south rift zones passing through the summit craters. The gravitation of the formation interacts with a fault system located in the lower slopes and offshore. It is worth mentioning that the investigated coastal sector is characterized by long and short-term tectonic uplift, what is in contrast with the general seaward sliding dynamic. Moreover, no evidence of sliding-related structures, for instance disturbed sediments, are documented in literature and found in our examined area. Volcanism is the foremost agent of insular growth and one that changes coastal outlines very rapidly and dramatically. The nature, intensity, and distribution of volcanism over space and time will condition the way volcanism shapes coasts. Effusive volcanism generally adds large tracts of land to island edifices, actively contributing to expanding shorelines. Paradoxically, explosive volcanism can simultaneously build and destroy coastal landscapes and contribute significantly to sediment production. The volcanic coastline from Catania to Capo Schiso and the northeastern shoreline from Taormina to Milazzo display widespread evidence of coastal emergence. The pattern of uplift suggests that the northeastern coastline of Sicily, including the volcanic edifice, is apparently uplifting as a coherent unit, with superficial flank movements being superimposed on a regionally uplifting subvolcanic.
Tonini et al. Summarised the eastern coast of Sicily and the tsunami risk imposed on it by the underlying faults of the Messina Strait. Although tsunamis occur very infrequently in this area, they have the effect of interrupting beach morphology and influencing rock stratigraphy. The last recorded major tsunami was in 1908 and had a run-up height of 10 metres. This destructive wave would have easily been able to destroy the Alcantara's river delta, upturn beach morphology and displace large boulders. It is unlikely that any evidence from the tsunami would have impacted our study and been visible in the field, although we did find large boulders in the rock stratigraphy in the mouth of the Fiume de Alcantara, which may have been deposited by the tsunami wave. Although we didn't find any seashells or other tsunami deposits, so it's likely these rocks were deposited when the Fiume de Alcantara was in a high flow period. The management strategies at Gardini Naxos aim to slow the rate of longshore drift and will therefore impact what we see at the beach. Between the 1970s and 2000s, eastern Sicily underwent mass erosion at a peak narrowing of 5 metres per year between 1967 and 1972. 17 intervention projects were implemented as a result with varying success. Randazzo et al. Concluded that the success of these schemes had been limited due to technical problems and poor planning. Randazzo doesn't conclude how effective the management has been in terms of volume of transported material, so we cannot quantify the effect the management has had on Capo Schiso. The rate of longshore drift can be expected to decrease with further successful developments in Gardini Naxos, however.
What data limitations did you have?
Well, we couldn't really carry 2 ranging poles onto an EasyJet flight because they'd probably kick us off. So we had to use me and Maya as ranging poles, and she's a little bit taller than me, and we were the closest in height, so that was that. And we had 84 bags of sediment, which, I mean, with 2 days worth of data collection, you can't really sieve it all in one day, which we had. So we had to cut it down and do every other every other transect for our sediments.
What other limitations did you have?
Well, when you're working on a beach, you've got to consider the tides, and this meant that we had a shorter time to collect our data, and as we went along, our transects got shorter. So as we went from one river to the other river, our transects decreased in size, except for when we got to the last few, because we did those in the second day. But and part of the beach was made private by the hotel that was like right here in the video. You can see that big bit. The hotel made that bit of the beach private, so there was no effect of longshore drift there. And we went in February, which is just after the winter storm period, so there were big like boulders placed like in random places along the beach, which made things quite difficult for us.